Hello, my friends and colleagues. Today I would like to share some of my past analytical results on analysis of 40 PFAS in surface water using automated SPE and QSAT LCMS based on US EPA method 1633. In this presentation, I would like to address some of the analytical challenges for PFAS analysis, then discuss some requirements for method development, the key performance indicator, then discuss the key criteria for method validation. Finally, I'll show some results for the surface water analysis. So far, this EPA method is the most comprehensive method that covers 40 PFAS. And this is also the only PFAS method that have been extensively validated by different laboratories for non-potable water, such as surface water, wastewater, groundwater, and soil, solid, sedimental, biosolid, fish, shellfish tissues. This method is a so-called performance-based method. That means we can modify the method as long as we can meet the method criterion requirement. This method also is a isotope dilution method, so to ensure method accuracy and great precision. In this study, we used automated SPE for sample preparation and QSAT 420 for PFAS analysis. As we all know, PFAS is everywhere. Therefore, the biggest analytical challenge is to minimize the contamination and reduce the background. Another one is the sample matrix effect. So we need to develop a good LC method to separate the interference from the PFAS analyte. Also, for analyte identification and confirmation, we also use multi-MS transition to compare the ion ratio for the analyte confirmation. Another one is during sample preparation, we use SPE and graphite carbon black to clean up the sample to get rid of the matrix effect. For PFAS analysis, it is important to use a delay column to get rid of the interference component from the LC system, such as from mobile phase, from some part of the LC system. So it is critical to use a delayed column. I'll show you some results in the next slide. In addition, we also need to replace some plastic tube in the auto sampler with a PIC tube to reduce the background. This slide shows some examples why we should use a delay column. You can see on the right side the interference component. If we don't use the delay column, they could overlap, therefore affect the PFAS result. In the following slide, I would like to show some of the key performance criteria during LCMS method development. In our study, we have found that methanol as organic mobile phase can boost the sensitivity compared with acetone nitride. However, using methanol as mobile phase and with a carbon-18 column, we cannot meet the requirement for separation for the Cholic acid or bile acid from the PFOS. So the requirement by the method is a minimum 1 minute. You can see from this slide, the PFOS actually sandwich between this bile acid. Therefore, this cannot meet the EPA method requirement. When we use a different column, such as a phenolhexane column, still with methanol as organic mobile phase, we can see that actually this PFOS have completely overlapped with the first acid. Therefore, this condition cannot be used. Using a biphenyl column with methanol as mobile phase, you can see that PFOS peak are moved earlier again, actually moved earlier than those interference. Is a significant difference from the common 18 column. So this actually provides us an alternative selectivity for PFAS analysis. So if you really want to use methanol as mobile phase, I would suggest use this biphenyl column, because usually interference, when they come after the analytic peak, they have less effect for the analyte. Therefore, if you really want to use methanol, I would recommend you to use this biphenyl column to boost the sensitivity. This slide compares the difference of using methanol and acetonitrile as mobile phase with a carbon 18 column. You can see that on the right side with acetonitrile as mobile phase, the cholic acid can be separated from the PFOS completely with roughly 2 minutes separation. So this meets the requirement by the EPA method, the 1 minute requirement. This slide compares the column side on separation. The left side is using a 4.6 ml ID column. The right side uses a relatively smaller ID, 3.0. So due to the column capacity in the left side, they can not only separate the interference from the PFOS better, they can also separate the PFOS and isomer much better compared with the smaller ID column. For PFAS, which have linear and branched isomers, EPA method require we have to separate them, and also we have to report them as a single result. Therefore, when you integrate, you need to integrate all the peak together, get a result. So this slide shows the separation and the calibration. Currently, there are 11 PFAS available. These are standard available. They have both linear and branched isomers. Therefore, EPA require, as long as you have this standard available, you have to show the separation and quantifications. So here we show another two PFAS. They have linear and branched isomers. Here is another two PFAS. Another two PFAS which have linear and branched isomers. Another two PFAS shown here. This slide compares the ionization energy on PFAS signal. So we found that as a lower ionization energy, the smaller PFAS actually have a better signal. With the increase of ionization, the long chain, less polar PFAS have better signal. This slide shows the result of a different concentration of ammonia acetate on PFAS signal and the retention time. You can see with the increase of the concentration, PFAS retention time slightly increase. However, the signal intensity do not change much. Therefore, to prevent the salt precipitate on the column in isonitrile mobile phase, so it is recommended to use a lower concentration, such as 2 millimole or 5 millimole, because salt solubility in isonitrile is low. So in this study, we use a relatively large ID column, such as a 4.6 column. So in this column, using this column, we can inject a relatively large volume of sample without change the peak shape. You can see compare 3 microliter and 6 microliter, the peak shape very good. Even we can inject up to 10 microliter, the peak shape do not change anything. So this is you can inject large volume of sample to increase your sensitivity of the method. So this slide just shows the 40 native PFAS separation after we optimize the LC-MS conditions. So this slide shows the 24 extract into the stand PFAS separation. This illustrates the 7 null extract into the stand separation. The following slide I will discuss the validation criteria, such as method selectivity, analytic confirmation from real samples, instrument sensitivity, method detection limit, sample metric effect, and extraction efficiency and method accuracy. Method selectivity can be evaluated by comparing the retention time and ion ratio of analyte in the reference stand and in the sample. Our software can automatically calculate the ion ratio when you integrate the peak. When you integrate both a quantum ion and qualifier ions. This slide shows another example with PFAS which have the linear and branched isomers. When you calculate both the quantifier ion and the qualifier ion, then you can generate the ion ratio. By comparing the retention time and the ion ratio, you can identify and confirm the analyte. According to this EPA method, the instrument sensitivity or the limit of quantification can be evaluated by signal to noise ratio larger than 10 in this study. And the method detection limit are calculated based on this equation. When you measure at least 7 blank or the lowest sparked samples, lowest LFM samples, at least 7 replicate. So here we actually did 9 replicate. Therefore, we use this equation to calculate the method detection limit. This slide shows some of the PFAS results, the LQ and method detection limit compared with the EPA method. We can see that all our results are lower than the EPA method results. Sample metric effect can be evaluated by the recovery of the null extract into the stand in the relatively pure sample, such as the QC sample prepared in reagent water and the real surface water. You can compare the recovery. So if the recovery is lower, that means you have a metric suppression effect. If it's higher, you have enhancement effect. So all our recovery meet the EPA method requirement. Method extraction efficiency can be evaluated by measure the recovery of the extract internal stand, because the extract internal stand actually spark before you spark to the sample bottle before you do sample preparation. So you can compare this recovery in the QC sample and in the real surface water to see the recovery. So our results meet the criteria set by the EPA method. Method accuracy can be evaluated by the analytic recovery. This 40 PFAS recovery from QC sample and from the field surface water samples. Since it's an isotope dilution method, all the PFAS recovery are great, all close 100%. In addition, we also did a proficiency test sample. All the results are within the accepted range. So if you are interested to learn more or want to see the result, you can shoot me an email. I can provide the result to you. In the next few slides, I will show you the result of surface water sample analysis. So this slide shows where I collect the surface water samples. I collect mainly from the water around the Lake Ontario, because Lake Ontario, the water is used for drinking water for many other things. So it's very important to know if this water contaminated. So I collect 4 waters from 4 different areas in Lake Ontario, and another 3 water samples collected from Mimic Creek, Humber River, High Park, that pond. Just want to say, all these water they are flow into the Lake Ontario. That's why I want to see which part has a big effect. This slide shows when sample chromatogram from one of the surface water samples. You can see 10 PFAS have been determined in this sample. This slide just shows the integration of this PFAS determined. Similarly, another 4 PFAS was determined as shown in this slide. The PFAS content and the ion ratio are shown in this slide for these 7 surface water samples and the QC sample and blind. This slide shows the published results for Canadian fresh water, including the surface water. So our results are in very good agreement with this published result, and our results are at the low nanogram per liter level. The following slide will show some benefit of this workflow for PFAS analysis. The bottleneck of the method or the analysis is the EPA method using 500 ml of water to go through the SPE sample preparation. It will take roughly 1.5 hours to finish this SPE sample preparation. So this will significantly reduce the productivity. So in order to improve the productivity, if we can reduce the water needed, for example, reduce from 500 to 250 or even 100, then you can significantly improve your productivity. So in this study, we use a relatively large ID column so that we can inject relatively large amount of SAM on the column. For example, instead of inject 2 microliter, we can inject up to 6 microliter SAM on the column. So this will significantly increase the sensitivity. Therefore, it makes it possible to use less water samples. In addition, when you inject a large volume sample, your precision can also be improved. Your accuracy also boosts. After SPE, the EPA method requires that the sample need to be cleaned up by the carbon black using the dispersive SPE method. So we can see that the dispersive SPE method have several drawbacks, and also it takes 40 to 60 minutes. So they take time, and also you may get the poor precision due to the human error and the low recovery for long chain PFAS. So this is a problem. Also, the carbon black, the other powder, is messy. They can contaminate your work area. Although some people are using this cartridge carbon black, can get rid of this problem, but still there are 2 columns, so you have actual cost, and also they need extra time. So in this study, we use this so-called bilayer wax and carbon black into 1 column to reduce the time and also improve the precision and recovery. Using automated SPE can significantly reduce human error, therefore improve recovery and precision. So this slide briefly summarizes what we have done. So I will not read this. So if you are interested, you can read this. In short, we meet all the EPA method criteria with authentic surface water samples. And this workflow provides several advantages, especially you can improve the precision, accuracy, robustness, and also improve the productivity, because the bottleneck of the analysis is you're using 500 milliliter water, large volume. You go through the SPE, you take quite a long time. If you can reduce this to 250 or even 100 milliliter, you can significantly improve your productivity. In addition, using this large volume of water also can cost a lot of money. For example, you have to collect this money, collect these waters, then store this water in your fridge, then transport the water. So all this process costs money. Therefore, if you can reduce the sample volume use, then you can significantly improve your operation efficiency and reduce the cost, improve your productivity. Thank you for your time. I welcome your feedback, suggestion, and comment for my future work. You can send your comment to my email directly. Thank you for your time.